Well, we've taken a quick introduction to the digestive system in part 1 of our chapter 23 investigation, and now we're about to take another look at some more of the anatomy and function of the digestive tract. Here's a little cross-sectional image, micrograph of the esophagus, and we've seen a picture a lot like this in our slides in the laboratory course. This muscular organ, when empty, is kind of scrunched up like a flower, and when you swallow, then that expands the tube in a bolus, it's called, of the food and liquids can pass down through the esophagus by peristalsis. The epithelium lining the esophagus is a stratified squamous epithelium shown up here on the top of this micrograph. So up here we're in the esophagus. It's a tough, abrasion-resistant epithelium that can withstand the chafing of solid food being swallowed down by muscular action, because as cells tear off from the surface, more cells are constantly being produced to replace them. When we transition into the stomach, however, we immediately and starkly transition over to a simple columnar epithelium, and that persists all the way down to the anus. Anus itself is, of course, a stratified squamous epithelium like the esophagus. The process of transferring material from the oral cavity down into the stomach is a reflex process called deglutition. If we masticate some material, add some saliva to it, and are ready to swallow, we can move it back towards the pharynx, and when it strikes some sensory neurons in the oropharynx, on the back of the tongue, and on the soft palate, it'll initiate a reflex in which the epiglottis will fold down over the opening to the trachea, and then will stretch into the muscular esophagus, and a peristaltic wave of contraction will push the bolus, it's called, the material right down to the stomach. There's a sphincter, a muscular valve called the cardiac sphincter right here at the boundary between the esophagus and the stomach, and that will, as the wave of peristalsis approaches this area, that sphincter will momentarily relax, allowing the bolus to enter the stomach, and then it will clamp down again, preventing the movement of material, acid from the stomach up into the esophagus. The stomach is arranged in terms of its wall structure the way, just like what we saw in the previous schematic, except that it has a third muscularis external layer, the so-called oblique layer. The stomach has such a job to do in terms of mechanical mixing and churning, that there's an extra layer of smooth muscle to really be able to do all kinds of maneuvers. When the stomach is empty, the lining is all shriveled up into ridges called rugae. So this term right here, and on the surface, of course, is the mucosa, the mucous membrane, I should say. So the whole mucosa is shriveled up into this wrinkly pattern. It's what allows the stomach to expand so much. When it's empty, it holds very little volume at all. And then when it's full, it may hold a couple of liters of fluid and food stuff. So the cardia of the stomach is this area here, and includes the cardiac sphincter, a muscular valve. The fundus of the stomach is kind of like a storage area. When you eat, if you eat a large volume, your stomach musculature can kind of hold stuff up there in the fundus and work with some material down here in the antrum and in the pyloric antrum here, and digest and mix and churn, and as we'll see, pass things into the duodenum. There's a valve or sphincter here between the stomach and the first part of the small intestine, the duodenum, and that's called the pyloric sphincter. And as we'll see, that waves of peristalsis will also cause or waves of muscular action will cause that valve to open. So we just mentioned about that. Here's a homeostatic imbalance of some interest and some prevalence in the population. In many people's experience, some of the stomach acid will find its way past the cardiac sphincter up into the esophagus, and if that happens repeatedly, it starts to cause inflammation in the esophagus because it's not suited to protect itself from stomach acid. And so inflammation occurs, and severe inflammation may arise in situations where there's just constantly this regurgitation or reflux of material from the stomach into the esophagus. A hiatal hernia is an anatomical abnormality in which the valve itself is above the level of the diaphragm. And we know that during inspiration, we inspire air by creating a negative pressure in the thorax, which serves to bring air in, but it also draws blood back to the heart and lymph fluid to the thorax. Well, unfortunately, if the valve is above the diaphragm, as it should not be, then that draws stomach acid up out of the stomach up into the esophagus and causes chronic inflammation in the esophagus, can even lead to esophageal cancer. Chronic inflammation or irritation in your body can oftentimes lead to cancers. Well, in the wall of the stomach, we have the three muscular layers, but we also have a lot of glands, secretory glands, and the glands have what are called pits, a neck part of the gland that just forms a passageway from the stomach contents down into the gland. And then we have all the gland cells lining this gland down here. We'll take a look at them in a second. So we see all these pits, they're called, in the wall of the stomach that give way to these glands. These are mucosal glands, as we'll see later on, or as you probably saw in lab. The place where there's a lot of glands in the submucosa is in the duodenum. But these very elaborate glands are actually all in the in the mucosa. Here's the muscularis mucosa, so we know we're in the mucosa because we have not yet crossed over this thin layer of smooth muscle. Here's the submucosa here. So here's a closer look at the stomach glands. And there's three kinds of cells we're going to pay attention to in here. Parietal cells produce hydrochloric acid, which acidifies the stomach contents, an intrinsic factor. The chief cells produce a inactive peptidase, or a enzyme that breaks down proteins, protease, another word for it, protease. And so pepsinogen is an inactive protease, which will then come out into the stomach contents. And finally, we have enteroendocrine cells. There's hormone-secreting cells here in the lining of the stomach glands. There are actually enteroendocrine cells, or so-called neuroendocrine cells, throughout the entire GI tract, sprinkled along the way. And in this case, they're very important for helping control stomach function. So those chief cells produce pepsinogen, and pepsinogen is inactive because you don't really want to digest the gland. You want to wait until the protease gets into the stomach, and it will then be converted to the active enzyme pepsin by hydrochloric acid, which then can start digesting protein. So we started chemical digestion in the oral cavity with saliva, which has amylase. Now we're adding to that pepsin in the stomach, and there are also amylases secreted in the stomach, so we're starting to add protein digestion. Lipases, I meant to say, are also added in the stomach that start to begin to digest fats, triglycerides, and we'll take a look at that another time. And this is just a little diagram illustrating the conversion of pepsinogen into pepsin through the action of hydrochloric acid. Incidentally, pepsin has its enzymatic activity to break down proteins predominantly at acid pHs. So it's made to work at acid pHs. Most proteins are not at all happy at acid pHs, but pepsin is made to be there. Enteroendocrine cells release a hormone called gastrin, and we'll talk about that in a little bit. I just want to quickly remind you about intrinsic factor. I glossed over that because I knew this slide was coming up. Intrinsic factor is a peptide or glycoprotein produced by the parietal cells that's needed for absorption of vitamin B12 in the colon, the small intestine and colon. So you've got to have this to absorb this important vitamin, because if you don't have that vitamin, you can't produce red blood cells normally, and you have a potentially life-threatening condition called pernicious anemia, not making enough red blood cells. This is a great illustration of how exactly the parietal cells can produce hydrochloric acid in the stomach. And it's actually going to be very familiar because it's the same chemical reactions by which the lungs can or the blood can carry CO2 in the form of bicarbonate ion, and the lungs can blow off that CO2 and help us manage the blood pH. All right, so what do we got? CO2 plus water is converted to carbonic acid by the enzyme carbonic anhydrase, just like we saw is in the red blood cells, and also in the brain stem, where we sense the CO2 content of blood through the central chemoreceptors. Anyway, the carbonic acid can dissociate into hydrogen ions and bicarbonate ions, as you know, and in this case, the hydrogen ions are going to be pumped and transported into the lumen of the stomach, and as well as chloride ions. The hydrogen ions are going to go in exchange for potassium ions, which then sort of do a little loop-de-doop, and we wind up in that movement of hydrogen ions into the lumen of the stomach, along with chloride ions coming from the blood. Right, we have this charge balance now that's occurring. What happens to the bicarbonate ions? Well, the bicarbonate ions are transported into the blood. We have to have something to do with them. They can't all reside in these cells as they continue to produce hydrogen ions. So we just take the two components from dissociation of carbonic acid, hydrogen ions into the stomach, bicarbonate into the blood. That's called the so-called alkaline tide. After you eat a meal and you produce a lot of acid in your stomach, you can measure a significant increase in bicarbonate ion concentration in the blood. Okay, so back to the enteroendocrine cells. There's enteroendocrine cells in the lining of the GI tract. The lamina propria receives chemical messengers from these endocrine cells, which then goes into the blood. Some of these substances that are produced by enteroendocrine cells include gastrin, a very important hormone called gastrin. Some substances produced by cells in the lamina propria, or secrete substances in the lamina propria that act locally, such as serotonin and histamine. They have important roles in controlling the function of smooth muscle in the wall of the intestine, as well as the secretion of acid in the stomach and hormones. The mucosal barrier is part of the innate immune system. It's the boundary between the outside of the body and the inside of the body, and there's a thick layer of, in the stomach there's a thick layer of bicarbonate-rich mucus that protects the mucosa from stomach acid. You can't have too much stomach acid touching the cells in the connective tissue. It'll destroy it. So there's a thick layer of bicarbonate. Bicarbonate ions obviously can neutralize stomach acid, so that if hydrogen ions begin to try to diffuse into the mucus, then they're neutralized by bicarbonate, and we just keep on producing new, fresh mucus on the surface of the stomach. Epithelial cells are constantly replaced, so that it's a very rough business being a gastric epithelial cell, and they're replaced every week or less than every week. You could have inflammation of that stomach lining, right? It's very vulnerable. There's a ton of acid in the stomach, and you have this mucosa underneath this layer of mucus. If it gets inflamed in there, it's called gastritis. If somehow some of the stomach contents begins to penetrate that mucus lining, of gastritis. If things persist, you're actually going to have a sore. An ulcer is called an erosion, and it's actually breakdown of the tissue in the wall of the stomach. Worst case scenario, it'll perforate, meaning stomach contents can burst right through the wall out into the peritoneum, and then you have inflammation there called peritonitis. Bacteria and acid and all kind of stuff is going to go in there. This is definitely a life-threatening condition, also hemorrhaging, broken open blood vessels, and so forth. Well, this horrible condition is most often caused by a bacterial infection, a particular bacteria called Helicobacter pylori, which can colonize the mucus of the stomach lining, and then in fact begin to colonize the wall of the mucosa. Aspirin, right? If you need to take aspirin long-term on a regular basis, you risk causing an ulcer in your stomach, because it's very irritating to the stomach lining and may actually cause stomach ulcer. Here's just an actual micrograph of a gastric ulcer, a sore formed in the lining of the stomach where you can see the tissue being eroded away. Here's just a micrograph of some bacteria, some Helicobacter pylori bacteria that are going to cause this problem. What are the digestive processes taking place in the stomach? The stomach is an extremely versatile muscular churning, mixing, and grinding organ. And so we have mechanical digestion happening in the stomach. We have denaturation of proteins. As I said, proteins don't really like acid conditions. They tend to come all unraveled under those conditions, and that allows enzymes to get at them. Pepsin is produced by the stomach and begins to digest proteins. We also have some lipases being secreted in the stomach to break down fat, triglycerides. The stomach is then going to deliver the solubilized, mainly solubilized material into the duodenum. And then it's called chyme at this point. Now I'm going to refer to it as chyme, the stuff in the lumen of the GI tract. Once again, just how important is this? Well, just to reiterate, we already mentioned intrinsic factor coming from the parietal cells in the stomach is needed for absorption of vitamin B12, which is in turn needed for production of red blood cells in the red bone marrow. So if you don't have enough vitamin B12 coming in, you have pernicious anemia. The thing is, intrinsic factor production declines with age, and elderly people tend to not produce enough intrinsic factor, and they tend to have a risk of pernicious anemia, a very bad situation. You need to either inject vitamin B12 into the blood or use a suppository either in the nasal cavity or in the rectum to let vitamin B12 cross the epithelial membrane into the blood and get that situation taken care of. Okay, so join me next time and we'll talk about the regulation of the stomach activity. We know it's a muscular churning organ. We know it secretes all kind of good stuff. What controls all that? And then we'll start looking at the anatomy of the intestines.